Hello everyone. Let us discuss some special filters, and these are known as the Nyquist and half band filters. Half bands will be a special case of Nyquist filters. Now, these are special filters which deal with topics where sample rate conversion and multi-rate operations would be involved. Let's look at the motivation to the Nyquist filters, and it stems from polyphase decomposition. Consider the factor of capital M interpolator shown below, in which xn is the input and xn is upsampled with a factor of capital M, and hz is the low pass filter, yn is the output. Now, the input output relation of the interpolator in the z domain is given by yz will be equal to hz x of z to the power m. So this is how we can mathematically represent an interpolator in terms of its output and input. That is yz equal to hz x of z to the power m. Now we know that this is the direct implementation of hz. Now if we decompose the transfer function of the low pass filter into its polyphase components, then hz is realized, and if we select capital M polyphase components, so it will be called as capital M band polyphase form. So that means hz is now represented in its capital M polyphase components, where hz can be obtained by sigma of I equal to 0 to capital M minus 1. That's the index which will give us the different polyphase components. Z to the power minus I, this will represent the delay chain in the polyphase components. EI Z to the power capital M. So that's how we represent the direct implementation of hz into its polyphase components. Now, if we expand this sigma term, then we will get the first term equal to I equal to 0, second term I equal to 1, this term corresponds to I equal to k minus 1, this term is I equal to k, and this term is I equal to k plus 1, and this is I equal to capital M minus 1. Now we assume that the kth term is constant. In the realization, in the polyphase decomposition of hz, we assume that the kth term is constant, right? That means ekz is alpha. So that is why we can represent this kth term as alpha z to the power minus k. So this is the delay chain, because the delay element will be there. Sorry, the delay element will be there, right? And the delay element will be there, and the rest of the things are constant, and we put it equal to alpha. Now, how to get yz from the polyphase components? We know that yz is equal to hz x of z to the power m. Then, because this is the kth term, and we have assumed that the kth term is constant, so alpha z to the power minus k represents the hz part of kth term, and xz to the power m is the because we have to go for yz. So this is basically corresponds to the kth term, and this rest of the values of I, where I not equal to k, because kth term is this when I is equal to k. So rest of the values are represented by this part, where sigma I goes from 0 to capital M minus 1 and I not equal to k. The rest of the components remain the same. This xz to the power m factor will come, because this is the hz part for all the terms except I equal to k, of course, and it has to be multiplied with the xz to the power m to get yz, right? So this is the case when the upsampling is done. Now, if we downsample and we want to recover the signal xn back, then we can recover if we then we can if we take the inverse set transform, and we can take the difference equation, and we can recover xn signal. So ymn plus k will be equal to alpha xn. Thus, the input samples appear at the output without any distortion for all values of n. So, because alpha is a constant, so what is output? Output will be equal to xn. So that means all the output samples, um, all the input samples appear at the output with no distortion, because this term y equal to alpha, which is a constant, into xn. That means we are able to recover all the samples, right, at the output without any distortion for all values of n, and all the rest of the capital M minus 1 output samples will be determined by interpolation. Now this figure shows a typical impulse response of a third band filter where capital M equal to 3. Now, if you see that this is the third sample, this is again the third sample, this is again -6, which is the third sample from here. So these will be all will be zeros. So that means there will be lots of zeros in the impulse response of the M band filters, which are basically known as the Nyquist filters. Now, the M band filters can be implemented either through a FIR structure, or it can be implemented through IIR approach, right? Now, a filter with the above property is called a Nyquist filter or an mth band filter. Important thing is that its impulse response has many zero valued samples, and the advantage will be we will get a computational advantage out of that, because if the number of samples are zeros, then the multiplication of the multiplication will yield into zero values, so make it computationally very attractive, because we know that once the once the once the input will be multiplied with the zero impulse response, then we get zero. So computationally, it is very attractive scenario to have many zeros in the impulse response. Now, for example, the impulse response of an mth band filter for k equal to 0 satisfies the following condition. When we put k equal to 0, we can say that HMN, right, will be equal to C. That's a constant value for n equal to 0 and 0 otherwise. We know that this, if we use this equation and we put k equal to 0, we know that y of mn will be a constant value. And let's say we choose a constant C for n equal to 0 and 0 otherwise. So that's the basically mth band impulse response of the mth band filter, and which will be known as the Nyquist filter. All right. Now, if we dig little deep into the Nyquist filters, then we can say that sigma k going from 0 to capital M minus 1, h of z omega m k, omega subscript capital M superscript k. Actually, these are, if we look at the frequency response of the component, if we look at the frequency response of hz in terms of the polyphase components, we know that this factor actually represents the frequency components, right? And we can interpret this as a DFT. We can interpret from our DFT as filter bank, and we can say that these are basically translation. These are basically translation of frequencies. Now, if we take the integer multiples of frequencies and then translate the frequencies, right? And if we add these frequencies, that's what this factor represents. sigma k going from 0 to capital M minus 1 h of z w m k. Now, if we expand this factor, right, for various values of k, in that case, the and if we decompose h, the direct implementation of h into m polyphase components. So for k equal to 0, we will have m components. With the first component, we assume it equal to 0. We assume it equal to constant. So this first row will be for k equal to 0. All these are to be added, right? For k equal to 0, we have this equation. For k equal to 1, we will have this equation where omega minus 1, here omega will be 0, here omega will be minus 1. We are taking the inverse roots of unity, inverses of the nth roots of unity, and this is for k equal to 1, and this factor will be for k equal to capital M minus 1. If we expand this term, which is the sigma k equal to 0 capital M minus 1 h of z w m k, m subscript m and superscript small k. Now, if we add all these terms, what we will get is this is c, this is c, this is c. How many c's will be there? M c's will be there. So we will get a factor cm. And if you look at the rest of the factors, you will see that this will be z to the power minus 1, right? Z to the power minus 1, z to the power minus 1, z to the power minus 1, and you will also get 1 omega minus 1, omega m minus 1, minus m minus 1, and if you add these, all these terms, because 1 plus, or because these are the inverses of the nth root of unity, all these terms, rest of the terms will go to 0. If you analyze this part, you will see that all the rest of the terms will go to 0. And this equation, sigma k going from 0 to capital M minus 1 h of z w subscript capital M superscript k will be equal to Cm, right? And if we put this constant term, which is C, equal to 1 by M, then what we will get is sigma of k equal to 0 capital M minus 1 h of this factor will be equal to 1. Now this is a very important relationship, and this is known as the Nyquist condition. Now let's look at now if you look at this factor, sigma k going from 0 to capital M minus 1 h of z omega m superscript k equal to 1. Now we can say that, as I already said, we can interpret from our DFT as filter bank concept that these are basically translation of frequencies. And if you consider integer multiples of frequencies and then translate and finally perform the summation of the spectra represented by this frequency translation of different frequency component, then they all add up to give flat spectrum, because this is constant. This summation gives me this spectra has to be added, this spectra of all the frequency components which are translated, right? And this will give me the flat spectrum. This is for the first component. This is for h of z wm. This is for h of z wm2. This is h of z w m minus 1. So that means all the spectra where the factor k goes from 0 to capital M minus 1, all the spectra will give me, because here if you will add up because these two spectra are superimposed with each other. Now if you will add up the two values, it will give you a complete flat spectrum throughout. So that's what the importance of this relationship is. Now in the M band filters, the spectra of all the filters will add up to a constant value, or it will be a flat spectrum. Now let us look at a special case of Nyquist filters. and this special case is known as the half band filters. Now in the mth band filter, we will choose capital M to be equal to 2 to give to result into a half band filter. Now the transfer function of a half band filter is thus given by hz equal to alpha plus, because the first component we have assumed to be constant, plus z to the power minus 1 e1 z square, because it was z to the power in the general equation, it was e of z to the power m. So because we are considering the capital M to be equal to 2, so this will be e1 z to the power 2, because in general case it was z to the power m, so here it will be 2, and its impulse response will be given by you will get from this equation, h of mn, and this is the equation um, from where we have got this value, this, because only two components will be there, h side alpha, this is the constant term, and this is the second term, only two polyphase components will be there, and h of 2n will be equal to alpha, or we can put it equal to c. So right, this is a constant, alpha or c represents the constant term, h of 2n is alpha, n equal to 0 or 0 otherwise. Now this half band filter will have only two components, right? And the spectra of these two filters will be represented by e j pi by 2 minus theta, and h of e to the power j pi by 2 plus theta, and these two spectra add up to 1 for all theta. Or in other words, the frequency response of this exhibits a symmetry with respect to the half band frequency pi by 2, because um, corresponding to the pi by 2 frequency, they exhibit a symmetry, and hence the name half band filter is there. Now this will be the frequency response of the half band filter. Figure below illustrates this symmetry, and what is the meaning of the symmetry here? You will see that for this half band low pass filter, um, right, the pass band and stop band ripples will be equal. If you see, this is the pass band ripple, and this corresponds to the stop band ripple, so they will be of equal values in the pass band and the stop band. So that means delta p will be equal to delta s, and pass band and stop band edges are symmetric with respect to pi by 2. So this is the passband edge, right? This is the passband frequency, which is omega p, right, corresponding to the minus 3 dB attenuation, right? At this point, if you get the frequency value, you will get it to be equal to omega p, and at this point, corresponding to this delta, which is the stop band attenuation, corresponding to this, you will get the stop band edge, right? So passband edge and the stop band edge, they are symmetrically placed from each other with the center value of pi by 2. So that is why these filters are known as half band filters, and we will see that omega p plus omega s will be equal to pi. So that's the relationship between the passband edge and the stop band edge. So this is a special case of Nyquist filter, which is the half band filters. So this finishes the special type of filters uh, to be which come under the category of Nyquist filters, right? These filters will be used at various places where the sample rate conversion will be required, and the multi-rate operations will be involved. And the advantage of these filters will be that the impulse response of these filters involves lots of zeros. So what is the advantage of having zeros in the impulse response? That when you have the coefficient values of these filters to be zero, and when certain input comes, so you know that when these filters will be multiplied with the input input values coming, so they will result into zero. So computationally, that is a very attractive package to have zeros in the impulse response. And these filters are basically used for that purpose. uh, to make the system, your resultant system will be less complex. The complexity, to reduce the overall complexity of the system, you incorporate these special filters in your system. Thank you.